There is a number that I want to give you right at the start of this conversation before I explain where it comes from or what it means. Because I think the number itself, just sitting there, does something that all the explanation in the world cannot quite replicate. The number is 46,508,000,000. 46,508,000,000. That is the current radius of the observable universe in light years. Not the distance to the most distant thing we have ever detected. Not the distance light has traveled since the Big Bang. The actual, current, physical distance from where you are sitting to the edge of the region of the universe from which light has had time to reach us. Most people, when they first encounter cosmology, assume this number should be about 13.8 billion light years because the universe is 13.8 billion years old and nothing travels faster than light. But you already know, if you have been watching this channel, that space itself expands, that the expansion carries distant objects away from us faster than light, and that this means the observable universe is much larger than a naive calculation would suggest. The light that is just now reaching us from the most distant galaxies left those galaxies when they were much closer to us, when the universe was much younger and much smaller. In the time it took that light to reach us, the universe expanded, and the galaxies that emitted it are now much further away than 13.8 billion light years, 46.5 billion light years. That is the edge. That is as far as we can see, in principle, with any instrument, at any wavelength, with any technology we could ever build. Beyond that edge, the universe almost certainly continues, probably forever. But we cannot see it, because the light from beyond that edge has not had time to reach us. We are isolated not by walls, but by time, by the finite age of the universe and the finite speed of light. The observable universe is our cosmic horizon, our information boundary, the limit of everything we can ever directly know about the physical world. And the James Webb Space Telescope has been looking at the structure of that universe, from the earliest galaxies near its edge to the large-scale patterns of matter across its volume, with a precision and a depth that no instrument before it could achieve. And what it has found, accumulated over years of observation and published in a series of papers that have sent quiet tremors through the cosmological community, is something that I find genuinely alarming in the most productive sense of that word. Not alarming as in threatening, alarming as in the kind of thing that demands you stop and reconsider what you thought you knew. The structure of the observable universe at the largest scales does not match what our best model of cosmology predicts it should look like. The discrepancy is not small. It is not at the edge of statistical significance. It is systematic, it is growing as the data improves, and it is pointing toward a conclusion that most cosmologists are not yet ready to say out loud in public, but that is becoming increasingly difficult to avoid. Our model of the universe, the model that has been the foundation of cosmology for decades, the model that explained the cosmic microwave background and the abundance of light elements and the distribution of galaxies and the accelerating expansion, may be missing something fundamental about the structure of reality at the largest scales we have ever probed. I want to take you through what James Webb found, why it matters, and what it might be telling us about the universe we live in. Not with the breathless urgency of a news article looking for clicks, with the care and the honesty that the data deserves. Let me start with what the standard model of cosmology predicts about large-scale structure, because understanding the prediction is necessary for understanding why the observation is so significant. The standard cosmological model, Lambda-CDM, describes a universe that began in a hot, dense, nearly uniform state at the Big Bang and has been evolving ever since under the combined influence of gravity, dark matter, dark energy, and the known forces of particle physics. The tiny fluctuations in density that existed in the early universe fluctuations that we can see directly in the cosmic microwave background as temperature variations of about 1 part in 100,000, were the seeds of all the structure we see today. Gravity amplified those fluctuations over billions of years, pulling matter into denser regions, forming the first stars and galaxies, assembling those galaxies into clusters and superclusters, weaving the large-scale structure we call the cosmic web. The cosmic web is the largest structure in the universe. It consists of filaments, vast threads of matter, hundreds of millions of light years long, connecting clusters of galaxies at their intersections with vast empty voids between the filaments from a great enough distance. If you could see the whole cosmic web at once, the universe would look like a three-dimensional foam or a vast neural network, with matter concentrated along the edges of bubbles and nothing in the interiors. The Lambda-CDM model makes precise predictions about the statistical properties of this web, about the typical size of the largest structures, about the spectrum of fluctuations on different scales, about the degree of homogeneity, the smoothness of the matter distribution when averaged over volumes larger than a certain scale. That scale is called the scale of homogeneity, and Lambda-CDM predicts it should be approximately 250 to 300 million light years. Above that scale, the universe should look statistically the same in every direction. The fluctuations should be small. The distribution should be smooth. The cosmic web should have no preferred scale larger than a few 100 million light years. This prediction has been tested by every large-scale survey of galaxy distributions for decades, and for decades, the agreement has been good. The Sloan Digital Sky Survey, the 2-degree field galaxy redshift survey, the Wiggle-Z dark energy survey, all of them found a universe that looked at the largest scales they could probe, consistent with the predictions of Lambda-CDM. But James Webb can see further, much further. And at the scales that James Webb can probe, the agreement is not good. Let me tell you about the specific observations that have generated the most concern in the community, because the details matter and they are more interesting than the headline. The first and most striking observation involves the number and mass of massive galaxies in the very early universe. Lambda-CDM predicts that galaxies assemble hierarchically, that small galaxies form first and merge over time into larger ones, that the most massive galaxies should be relatively rare in the early universe and more common in the late universe. The model makes specific quantitative predictions about the number density of galaxies of different masses at different cosmic times. James Webb has been observing galaxies at redshifts of 10, 12, 14, corresponding to times when the universe was only 300 to 500 million years old. And it has found galaxies that are far more massive, far more mature, far more numerous than Lambda-CDM predicts should exist at those times. Not by a factor of 2 or 3, by factors of 10, 50, in some cases more than 100. Galaxies that look like they have been forming stars for billions of years in a universe that had only existed for hundreds of millions, these are not marginal detections. These are clear, high signal-to-noise observations of galaxies that are unambiguously present in the early universe at masses that the standard model cannot easily accommodate. The initial James Webb observations suggested the problem might be smaller than it first appeared, that some of the apparent masses might be overestimated by the photometric techniques used to measure them. But subsequent spectroscopic confirmations, direct measurements of the redshifts and stellar masses of specific galaxies have confirmed that the problem is real. The galaxies are there, they are as massive as they appear, and Lambda-CDM struggles to explain how they got there so fast. The second observation involves the large-scale distribution of galaxies and the structures they form. Lambda-CDM predicts the scale of homogeneity should be roughly 250 to 300 million light years. But James Webb, combined with data from other surveys, has been finding evidence for coherent structures at scales significantly larger than this. There are reports of galaxy filaments and walls extending over distances of several billion light years. There are reports of large-scale patterns in the distribution of quasars and galaxies that show correlations at scales that should, according to Lambda-CDM, be randomly distributed. There are observations of what appear to be preferred directions in the large-scale structure, alignments of galaxy spins and shapes over volumes so large that the standard model gives them an extremely small probability of occurring by chance. The most discussed of these is a structure called the Giant Arc, discovered in 2021 by Alexia Lopez and her collaborators using data from the Sloan Digital Sky Survey. The Giant Arc is an arrangement of galaxies, galaxy clusters, and quasars spanning approximately 3.3 billion light-years in length. It is not a simple filament. It is a curved arc of concentrated matter extending across a volume that should, according to Lambda-CDM, be statistically homogeneous. It should not be there. Or rather, the probability of a structure of that scale and coherence arising by chance within the Lambda-CDM framework is extremely small, somewhere around 1 in 50,000. A probability of 1 in 50,000 is not zero. It does not prove that Lambda-CDM is wrong. Rare events happen. The universe is large enough that rare fluctuations are expected to occur somewhere, but 1 in 50,000 is the kind of probability that demands attention. And the Giant Arc is not the only anomalous large-scale structure that has been identified. There is the Sloan Great Wall, extending approximately 1.4 billion light-years. There is the Hercules Corona Borealis Great Wall, reported to extend over 10 billion light-years, which, if confirmed, would be by far the largest structure ever identified in the universe and would be flatly incompatible with the standard model. The status of the Hercules Corona Borealis Great Wall remains debated, with some analyses supporting it and others finding the evidence insufficient. But the accumulation of these reports, each individually explainable as a statistical fluctuation, is beginning to look less like a collection of coincidences and more like a systematic pattern. And then there is the Hubble tension, which I discussed in detail in the first video in this series and which has not gone away. James Webb was supposed to help resolve the Hubble tension by providing better measurements of the cosmic distance ladder, better calibrations of the Cepheid variable stars that anchor the local measurement of the expansion rate. Instead, the James Webb observations have confirmed and, in some analyses, sharpened the tension. The universe appears to be expanding faster than the standard model predicts, and better data has not made the discrepancy go away. It has made it more precise and more difficult to dismiss. What does it mean for all of these observations to be happening simultaneously? I want to think through this carefully because there are two very different ways to interpret the situation and they have very different implications. The first interpretation is conservative. It says that each of these anomalies has an explanation within Lambda-CDM or within modest extensions of it, that the massive early galaxies can be explained by more efficient star formation at early times or by modified assumptions about dark matter, that the large-scale structures can be explained as statistical fluctuations that we happen to be detecting because we are looking harder than ever before, that the Hubble tension will eventually be resolved by systematic effects in the measurements that have not yet been identified. This interpretation says that Lambda-CDM is fundamentally sound and that we are in a period of normal science where anomalies are being discovered and will eventually be resolved within the existing framework. The second interpretation is more radical. It says that the simultaneous emergence of multiple independent anomalies, all pointing in the same direction, toward a universe that is more structured at large scales and evolved faster at early times than Lambda-CDM predicts, is not a coincidence. That the anomalies are connected, that they are telling us something about the framework that is wrong, not about the data that needs to be reinterpreted. That Lambda-CDM is missing something, not in its details, but in its foundations. I want to be honest about where I stand on this. I think the conservative interpretation is still defensible. I think it would be premature to declare Lambda-CDM broken on the basis of the current data. The history of cosmology is full of anomalies that were eventually resolved within the standard framework, and the standard framework has proved remarkably resilient over the decades. I do not think we are yet at the point where the evidence is strong enough to abandon it. But I also think the radical interpretation deserves more serious attention than it is currently getting in the mainstream of the field. The pattern of anomalies is too coherent, too consistent in its direction to be completely comfortable. Multiple independent measurements using different instruments, different wavelengths, different analysis techniques are all finding a universe that is more structured, more evolved, more complex at large scales and early times than the standard model predicts. The probability that all of these measurements are wrong in the same direction due to independent systematic errors is not zero, but it is not large. What would it mean for Lambda-CDM to be fundamentally wrong? This is the question that I think is most important and most difficult to confront, because the implications are not minor. Lambda-CDM is not just a description of the distribution of galaxies. It is a complete account of the history and composition of the universe. It includes the Big Bang, inflation, the formation of the first stars, the assembly of galaxies, the nature of dark matter, the nature of dark energy, the ultimate fate of the universe. If the framework is wrong at the foundations, all of these things need to be reconsidered. The most likely candidates for what Lambda-CDM is missing involve the two components of the universe that we understand least: dark matter and dark energy. Lambda-CDM assumes that dark matter is cold and collisionless. Cold means that dark matter particles were moving slowly relative to the speed of light when the universe was young, which means they could cluster on small scales and seed the formation of the smallest structures. Collisionless means that dark matter particles interact only through gravity, not through any other force. If dark matter is cold and collisionless, its behavior is completely characterized by its gravitational effects, and it forms structures in a predictable, hierarchical way. Small halos first, then larger ones formed by mergers. But if dark matter is not cold, if it is warm or hot or self-interacting or fuzzy or composite, the formation history of structure changes. Warm dark matter suppresses the formation of small structures. Self-interacting dark matter can form denser cores in galaxies and modify the merger history of halos. Fuzzy dark matter, made of extremely light bosonic particles, has quantum mechanical wave properties that suppress structure on small scales and might produce very different patterns at large scales. Any of these alternatives to cold dark matter would change the predictions of the standard model in ways that might resolve some of the anomalies. Dark energy is an even more uncertain component. Lambda-CDM treats dark energy as a cosmological constant, a fixed energy density of the vacuum that does not change over time. But if dark energy is not constant, if it is a dynamical field that has evolved over cosmic history, the expansion history of the universe would be different, and the formation of large-scale structure would proceed differently. Some configurations of dynamical dark energy could allow structure to grow faster at early times, potentially explaining the massive early galaxies. Some could modify the expansion rate in ways that resolve the Hubble tension. The DESI survey, the Dark Energy Spectroscopic Instrument, has been accumulating data on the large-scale distribution of galaxies and the baryon acoustic oscillations, the regular patterns in galaxy clustering that serve as a standard ruler for measuring cosmic distances. In 2024, DESI released its first-year results, and they contained something that immediately attracted attention. The data showed weak but non-trivial evidence that dark energy may not be constant. The best fit cosmological model to the DESI data prefers a dark energy equation of state that evolves with time, becoming less negative in the recent past. This is not yet a definitive detection of dynamical dark energy. The statistical significance is not high enough to claim a discovery, but it is consistent with the direction that the other anomalies are pointing, toward a universe where the Standard Model's assumptions about its two most mysterious components, dark matter and dark energy, may be incomplete. There is a third possibility that I want to discuss, one that is more radical than modifications to dark matter or dark energy, and that connects to the deepest questions about the foundations of cosmology. The possibility that the initial conditions of the universe, the state from which everything evolved, are different from what we have assumed. Lambda-CDM is built on the foundation of cosmic inflation, the hypothesis that the very early universe underwent a period of extraordinarily rapid exponential expansion that smoothed out large-scale inhomogeneities, produced the nearly scale-invariant spectrum of fluctuations that seed structure formation, and set the initial conditions for the subsequent evolution. Inflation is not a single theory. It is a framework within which many specific models can be constructed, each with different predictions. The simplest inflationary models predict a universe that is extremely smooth at large scales, with fluctuations that are nearly the same on all scales, from the largest observable scales down to the smallest. But what if inflation was not exactly as the simplest models predict? What if inflation had features, departures from the simplest case that leave specific imprints on the large-scale structure of the universe? There are inflationary models in which the inflaton field, the field that drives inflation, undergoes transitions or has periodic features in its potential energy that produce preferred scales in the spectrum of initial fluctuations. If those preferred scales correspond to scales comparable to the largest structures we observe, they could explain the coherent patterns in the large-scale distribution of galaxies without requiring modifications to dark matter or dark energy. This is a relatively conservative modification in the sense that it still operates within the inflationary framework, but it has radical implications for our understanding of the very early universe. It means that the specific microphysics of inflation, the details of the inflaton potential, left detectable imprints on the largest structures we can observe. It means that the James Webb observations and the large-scale structure surveys are probing physics that occurred in the first tiny fraction of a second after the Big Bang at energies that no particle accelerator will ever reach. And it means that the number I gave you at the start of this conversation, 46,508,000,000 light years, is not just a measure of how far we can see. It is a measure of how deep into the physics of the very early universe we can probe, because the structures at that scale carry information about the conditions that existed when the universe was unimaginably young and hot and dense. The observable universe is not just a region of space, it is a record. A physical record of everything that has happened since the Big Bang, encoded in the distribution of matter, in the temperature and polarization of the cosmic microwave background, in the clustering of galaxies, in the large-scale structure that James Webb is now mapping with unprecedented precision. Every anomaly in that record is a potential message from the physics we do not yet understand. Every structure that should not be there is a clue to what the Standard Model is missing. Every galaxy that formed too fast, every filament that extends too far, every measurement of the expansion rate that does not match the prediction is a fingerprint of something real that our current framework cannot accommodate. I want to say something about what this moment feels like from inside the field, because I think it is important, and I do not think it is conveyed adequately by the technical papers and the press releases. The cosmological community is in an uncomfortable position. The Standard Model has been extraordinarily successful It has explained everything we have thrown at it for 30 years. The people who built it, who tested it, who refined it, have invested their careers in it. It is not easy to look at data that suggests the framework might be incomplete and respond with openness rather than defensiveness. The natural tendency is to explain the anomalies away, to find the systematic error, to propose the minimal modification, to preserve the core of the model. But the anomalies are not going away. They are accumulating, and the James Webb Space Telescope, with its extraordinary sensitivity and its ability to see further and earlier than any instrument before it, is producing data at a rate that is making the discomfort harder and harder to ignore. Every few months, a new paper appears confirming a previous anomaly, or reporting a new one, or finding that a proposed explanation within Lambda-CDM requires fine-tuning that makes physicists uncomfortable. I do not know whether Lambda-CDM is about to be overthrown. I do not think anyone knows that. The history of science is full of moments that looked like they were pointing toward a revolution and turned out to be pointing toward a correction. The anomalies could all be resolved within the standard framework with modest modifications. The massive early galaxies could be explained by better models of star formation efficiency. The large-scale structures could be explained as statistical fluctuations. The Hubble tension could be resolved by a systematic error in the distance ladder that nobody has yet identified. But the history of science is also full of moments when the anomalies were real, when they were telling us something true and important about the limitations of the current framework, and when the scientists who paid attention to them, rather than explaining them away, were the ones who made the next great advances. The ultraviolet catastrophe was a real anomaly. The perihelion precession of Mercury was a real anomaly. The missing mass in galaxy rotation curves was a real anomaly. Each of them looked, at the time, like something that would eventually be explained within the existing framework. Each of them turned out to require a new framework. The anomalies that James Webb is finding may be the same kind of thing. They may be telling us that the universe is structured in a way that our current model does not fully capture, that the initial conditions of the universe were different from what we assumed, or that dark matter behaves differently, or that dark energy evolves, or that something we have not yet imagined is responsible for the structures we see at the largest scales. And if any of these possibilities is correct, the implications for what we know about the universe are profound. The history of the cosmos, from the Big Bang to the present, the nature of its most abundant components, the ultimate fate of the expansion, all of it would need to be reconsidered, not thrown out. Reconsidered, refined, made more accurate, in the way that Newtonian mechanics was not thrown out by general relativity, but was revealed to be an approximation, valid in a specific regime, but incomplete at the extremes. The number at the beginning of this conversation, 46 billion, 508 million light years, is the horizon of our knowledge. Beyond it, we cannot see. Within it, we are learning things that do not fit the map we drew before we had instruments capable of seeing this far and this clearly. The map is changing, not because the territory changed, because we can now read it more clearly than before. You are inside that territory. The 46.5 billion light-year sphere centered on you is the entire physical universe you can ever observe. Everything that can ever reach you, every photon, every gravitational wave, every piece of information about the physical world will come from within that sphere. And what James Webb is telling us is that the structure of that sphere at its largest scales is stranger than we thought, more organized, more evolved, more complex. That is not a problem for you to solve tonight, but it is something to carry. The knowledge that the universe you inhabit is larger and stranger than the model we built to describe it. That the map we drew of the largest scales is being revised in real time by the most powerful telescope humanity has ever built. And that the revision is pointing not toward a simpler universe, but toward a more complex one. A universe that formed its largest structures faster than it should have. that is more coherent at the largest scales than it should be, and that is expanding at a rate that its own history cannot quite explain. Go outside tonight. Look at the Milky Way if you can find a dark sky. The band of light you see spans about 100,000 light years. The observable universe is 46.5 billion light years across. The Milky Way is to the observable universe what a single bacterium is to the Pacific Ocean. And within that vast observable universe, James Webb is finding structures that do not fit, patterns that should not be there. A cosmos more organized and more complex at its largest scales than the model we built from our small corner of it predicted. The number does not fit. The structures do not fit. The expansion rate does not fit. Something is wrong with the map. And finding out what is wrong, finding what the universe is actually like at its largest scales, is the most important project in cosmology right now. The James Webb Space Telescope is not finishing the map. It is revealing that the map we had was incomplete. And the territory, it turns out, is far stranger than we knew. If this changed something in how you see the observable universe, if the number 46.5 billion light years lands differently now, tell me in the comments. Tell me which of the anomalies you find most significant and why. Tell me whether you think Lambda-CDM is about to be revised or overthrown. And subscribe if you want to stay at the frontier where the observations are coming in faster than the theories can keep up.